the session, I just want us to recap or remind ourselves of what vertical projectile motion is and what exactly can be accompanied or be found with vertical projectile. So we know that if, let's say, an example, if an object is thrown out of the window, maybe a frog that is jumping or a ball that is being kicked around, all these can be regarded as examples of vertical projectile or basically projectile motion. So in most cases, they tell us that we must ignore the air resistance or the friction that is taking place within the space or within the direction of motion, so that our calculations can make sense. So there was a gentleman by the names of Galileo who made a study about vertical projectile motion, and initially it was just believed that when you throw something, it must just come back straight to the earth as long as you've thrown it, let's say, upwards. Okay. According to this gentleman, he believes any object that is thrown upwards or dropped or projected must always take some sort of a curve, sort of directional movement, which means that this object must have two components, the horizontal component and then the vertical component. So when we talk about vertical projectile, our main focus is basically the vertical component. Okay, so in all of this motion is affected mainly by the acceleration due to gravity, which is 9.8 meters per second. Okay, so we're saying at the same time the projectile can move horizontally according to the principle that this guy discovered. And then when we look at the combination of the vertical and the horizontal, that's when we can get the actual resultant projectile motion or graph. Okay, then what other thing that we need to also talk about will be the definitions that we normally come across, the terms or terminologies under vertical projectile. So number one is what we call the free fall. So any object that is acted upon by gravity. So any object acted upon by gravity is believed to be under free fall. Acted upon by gravity is said to be under, let's say, state of free fall. State of free fall. So in other words, this is motion that is entirely influenced by acceleration due to gravity. And then terminology number two, we can talk about a projectile. What is a projectile? So a projectile is basically the object that starts, an object that starts its motion. An object that starts its motion with basically an initial velocity. Okay, this does not mean that the object has to be just thrown upwards, or it covers everything. It can be thrown upwards, it can even be dropped, or any other scenario. And then we have what we call a trajectory. So a trajectory is basically the path that is followed by a projectile, or the path that is taken by a projectile. That is a trajectory. Okay, and then number four, we have the terminal velocity. So terminal velocity is more like the maximum velocity that is reached by a falling object. I'm just gonna summarize it and call it maximum velocity that is reached by a falling object or object under free fall. And then free falling objects, we said they are mainly influenced by acceleration due to gravity. Okay, so under vertical projectile, we have what we call scenarios that we're gonna focus on. Okay, we can, I don't know, I'll call these cases. So the first case is where we find an object thrown upwards. object that is thrown upwards. That is scenario number 1. And then what happens in that, what we need to know, we shall discuss that. Then 2, let's say this is thrown upwards, let's from the ground. Okay, and then scenario number 2, an object that is thrown upwards but from a certain height. Same scenario but from a certain height. An example, you stand on top of a tall building and then you throw something up. What happens? That will be like scenario number 2 or case study number 2. Then we also have case study number 3. And this case study, we look at an object that is thrown downwards. Object that is thrown downwards. So in most cases, from a certain height. From a certain height. An example, a platform, a cliff, or even a balcony. Okay, that is thrown downwards with some bit of velocity, whereby the initial velocity is not 0. And then number 4, what if the object is just released? Object is released or just dropped from a certain height, whereby the initial velocity is 0. That is case scenario number 4. And then lastly is case scenario number 5, an object that is released from a moving object. Object released from a moving object. An example, if you're in a hot air balloon that is moving upwards and then you drop something. So whatever object you've dropped is gonna possess the initial velocity. That will be the velocity of that air balloon. Okay, then the other thing that we also need to familiarize ourselves with is the Newton's laws of motion. Okay, we have quite a number and we just need to be really selective in which one to use. Newton's equations of motion. Newton's equations of motion. Okay, so we know that first equation, which is V final, is equal to V initial plus, you can say, acceleration times delta t. But in most cases, we're not gonna call it the acceleration. In this case, since the object is under the influence of gravity, that acceleration A is gonna be turned into the gravitational force, which is G. So in other words, it's gonna be V final is equal to V initial plus G delta t. Okay, where the G is gonna be 9,8. We're saying A is the same as G, which is 9,8 meters per second squared. This is equation number 1. So this can only be used if we don't have any displacement. So if there is no displacement that is involved, then that is the equation to use. Then case scenario number 2, or the equation number 2, if we have Vf squared must be equal to Vi squared, initial velocity squared, plus the 2a delta y. It can be delta y since we're just focusing on the vertical projectile. The distance moved is in the y direction. So this is equation number 2, and we only use this if we don't have any time. Okay, if you're not using time, then this is the equation to use. And then lastly, we have change in y, delta y is equal to Vi times delta t plus a half a delta t squared. But what we are saying is that the a is gonna be replaced with a g. In most cases, a is gonna be replaced with a g. Now, depending on the direction of motion, okay, because we need to take also consideration when doing that. So I usually prefer to take upward motion to be negative, okay, if it is upward, and then downward motion to be positive. So if we're focusing on downward, then this will be a plus, plus, and plus. Then if it's an upward motion, this can be minus, minus, and minus. That is my approach. It's also believed, we know it can also work, whereby someone can take the downward motion to be negative, okay, and then the upward to be positive. You just need to state your case. You'll always get the same answers in whatever calculations you're going to do, for as long as you maintain the signs that you deciding to go with. Okay, so having looked at that, I believe we're good to start with the questions. Okay, I'm just gonna go through some questions. If time allows, I'll cover as much as I can. Okay, question number 1. We're being told that a cricket ball of mass 156 grams is dropped from point A on a tall building that is 15 meters high, and then it strikes the concrete pavement, and then it bounces off. And then it bounces off. So this object is dropped, it falls, hits the floor, and then bounces off to a height of 4, maximum height of 4. Then they're asking us to calculate the velocity with which the cricket ball strikes the pavement. So for as long as an object is dropped, then the initial velocity is going to be 0. And this question is asking for the final velocity. So we're gonna say our initial velocity is 0, our final velocity is what we don't know, or what we're looking for. The only thing we've been given is the displacement, change in y, is being dropped from a height of 15 meters. Then we need to select which equation are we going to use. Since our focus is v final, we have the v initial and we have the displacement. So the equation to use would be the vf squared is equal to vi squared. Since the object is being dropped, we said I'm going to take positive to be the downward motion. This is 2g delta y. Then I'll do my substitution. So that's going to be our vi, which is 0 squared plus 2 times 9,8 times the displacement, which is 15. Okay, when I put that into my calculator, I'm just getting something like this is 2 times 9,8, is that true? And then times 15. So that gives me 294. So vf squared is 294, and then I need to find the square root. Okay, then the square root of my answer gives me 17,15 meters per second. Okay, that is question number 1. Then question number 2, 1.2. If the effects of air friction are not ignored, in other words, if they are put into consideration during the fall of the cricket, how would the value that you calculated here change? Will it be higher, will it be lower, or will it stay the same? So guys, what do you think? If there is resistance involved, if there is friction involved, what effects does friction have in the final velocity? So in this case, I'm gonna go for lower. Why? Because friction, we said, is a force that opposes motion. So for as long as it's trying to oppose motion, because the ball is falling downwards, friction will be acting upwards. So which means this ball is gonna fall with a lower velocity. Okay, and then 1.3, they're telling us that the cricket ball is in contact with the concrete for about 0.8 seconds. So that 0,8 is more of a reaction time. Okay, so if we ignore the effects of air friction and we're taking downward motion as positive, okay, calculate the impulse. What do we do when we are getting impulse? We know that from your momentum, impulse and stuff, you might have said that our F net is the same as change in momentum, the rate of change in momentum, something like that, delta P over delta T. Does that make some sense? F net is this. So when we talk of impulse, it's the change in momentum that we're focusing on, which means our change in momentum will be the F net times the delta T. But what is our F net? We know that F net can also be written as MA, M times the acceleration. And acceleration can also be expressed, since in this case we don't have the acceleration of the object, we can use the velocities, okay? And say the mass, which is V final minus V initial, divided by the time. Mass times acceleration, which is V final minus V initial over T. We can use that as well before we can get to the actual answering of the question. Okay, so I'm just gonna erase this and just start over. Okay, so what I need to first of all find, what is the initial velocity or the final velocity that we're focusing on. So for as long as the cricket ball is in contact with the pavement for this much, and we're taking downward, calculate the impulse of the cricket ball on the pavement. So our final velocity is going to be assumed to be a 0. Okay, as soon as this ball strikes the ground, and then takes some time. Okay, initial velocity, I don't know that. My G is gonna be 9,8, and then I'm going to look at what's this. I'm gonna look at my displacement to be, is it 4? Yes, I'll look at my displacement to be 4. It makes sense though. Yeah, displacement is gonna be 4. And then from Vf is equal to Vf squared is equal to Vi squared plus 2g delta y. When I try to do the substitution with the 0, this is Vi squared plus 2 times 9,8 times 4. So now as I'm finding the velocity with which the ball started to rise up. Okay, so we are saying the ball strikes. It takes some time just on the pavement, and then it goes up to a height of 4. Okay, so the velocity with which the ball left the ground or the pavement is what I'm looking for. So when I do the maths here, this is gonna be, why am I taking 4? Why am I taking 4? Because it's moving upwards now. So it's gonna be negative 4. Okay, so that is 2 times 9,8 times 4, which is 78,4. So 78,4 is equal to the Vi squared, and then I find the square root of that, which is 8,85 meters per second. So this is just the initial velocity with which the ball is going to leave the pavement. Then I'll apply my F net and delta P. Okay. So we know that our F net times delta P is equal to the change in momentum. And we said this change in momentum is the same as AM V final minus V initial. When we do the substitution, what was the mass of the ball? They mentioned something like 156 grams. Change that to kilograms, it will be 0,156. What is our final velocity? It's negative 8,85. Since it's moving upwards, we are subtracting the initial, which was our final when the ball was striking the ground, which is 17,15. 17,15, since it was taking the positive sort of direction. Okay, when I work this out, I'm just gonna get something like negative 4,056. This is mass, which is kilograms per meter squared. So since we're focusing on impulse, it's gonna be 4,056, but in which direction? It's gonna be upwards. Okay, then 1.3.2, they want us to get the net average force that is exerted. Okay, so since we know that our F net is delta P over delta T, our change in momentum is the negative 4,056, and we're dividing it by the time. The reaction time was 0,8 seconds from the information that we were given. So we divide it by 0,8. If that happens, then we're going to get negative 5,07 newtons. So this can also be written as 5,07, but upwards. Okay, so the force is going to act upwards. And then 1.4, they want us to sketch a position time graph. Now guys, we have different types of graphs when it comes to projectile motion. We have what we call the position time graph, we have the velocity time graph, and we also have what we call the acceleration versus time. Now we need to know how all of these look like. Okay, so if it's a position, in most cases it will take form of a curve, and then if it's a velocity time graph, we normally use straight lines to draw that. Okay, no, it's fine, we shall probably look at the different scenarios. So sketch the position versus time of motion, which can go from the moment it is dropped up until it reaches the maximum height after the bouncing. So what we need to remember, they said position time graph. So on our y-axis, we're going to have our positions, and then on the x, we're going to have our time. So this is position, which position can also be represented as the y. Okay, and the question is, at what height did the object start falling? Okay, this position is in meters, this time is in seconds. So the object started falling from a height of 15. Okay, and then the object dropped. We don't know the time it took, we don't even need it at the moment. Then this object took some time on the ground, on the pavement, and then it rose again for a certain height. Which height we said was 4. So for as long as we have this, then we're good to go. So position time graph will always be a curve or made of curves. So this is the reaction time. Okay, and then 1.5. The cricket ball is now replaced with a softer ball, okay, of similar mass. They want us to state how the net average force exerted by the concrete pavement on the softer ball. With your answer, it's meant to be 1.3.2. We need to write only greater, smaller, or stays the same. So one thing we need to know is that from F net being delta P over delta T, change in momentum, we know that this net force is inversely proportional to the time. So if we are dealing with a soft ball is going to take more time on the pavement floor. In other words, the reaction time is going to increase. Okay, so when the reaction time increases, the net force decreases. Okay, so we're going to say delta T increases, which decreases the F net. So in other words, state how the exerted force is going to say smaller than. Okay, so the answer will be smaller than, because delta T increases, which decreases F net, because we know that delta T is inversely proportional to 1 over delta T. Okay, guys, that is question number 1. Then question number 2, it's more or less the same thing. We've been given a position time graph of a tennis ball. Okay, how do we approach a question when a graph is being provided for us? So they're telling us that the position time graph of a tennis ball that was thrown vertically upwards from a second floor of a school building shown below. Ignore the effects of friction. Okay, the height of the second floor is 6.5 meters. The ball rises 0.9 meters from the height of projection. Okay, so from here up to this point, that is 0.9 meters extra. Okay, before it starts to fall to the ground, so which means maximum height, an extra 0.9 meters. Okay, write down the magnitude and direction of acceleration of the ball while it's moving upwards. So the acceleration of the ball will always be 9.8 for as long as it's under a projection or projectile motion. Okay, and this acceleration acts downwards. Regardless of whether it's projected up or down, it must always act downwards, since that is the initial direction of gravity. Okay, and then they want us to calculate T1, the time it takes the ball to reach the maximum height. Okay, one thing we know about maximum height is that the final velocity has to be a 0. That's one thing we need to know. Final velocity has to be a 0. So now, since we've been given displacements, we've been given the g's known to us, but we're focusing on the displacements. Let's say the distance traveled, Vy, is 0.9 meters. What else do we know? We know that our V initial, is it gonna be a 0? It was projected vertically upwards from the second floor. Okay, so I'm not gonna assume that. So I'm gonna use this equation, Vf squared is equal to Vi squared plus 2 g delta y, something like this. So we are saying at the maximum height, final velocity is 0. Is that true? Yes. But the question is asking for the time it takes. Let me see if I can get an equation that has time straight away, so that I don't have to waste a lot of time. This is vi delta t plus a half delta t squared. And then f is vi plus a delta t. I have that. Do I have the initial velocity? No, I have the initial position. It's not gonna make sense. So which means I need to first of all get the initial velocity. Okay, so my vf is 0, my v squared I plus 2. Now the g is going to be negative 9,8 because the object is being projected upwards. An upward projection, I normally take g to be my negative. Okay, and then times the distance that the object traveled, which is the 0,9. Okay, when I sort that out, when I multiply that, I'm just going to use this to be positive since I've already considered the g to be negative. Okay, that is 2 times 9,8 times 0.9. That gives me 17,64. When I transpose that, vi squared is equal to 17,64. Find the square root. So square root of the answer is 4,2 meters per second. So this is the initial velocity. So having obtained the initial velocity, then I can use this equation here, the first equation of motion, and say my final velocity is 0, my initial is 4,2 plus it's gonna be negative 9,8 t. I hope that makes sense. When I move, if I transpose, I have 9,8 t is 4,2. Divide by 9,8 over 9,8. Okay, so 4,2 divided by 9,8, I'm getting 0,428 seconds, which will be more or less like 0,43 seconds. Okay. That is 0,43 seconds. So that is that. That is being it in 2 steps. But someone can even use this second equation, this, since you're looking for t, and then you get that straight away. Okay, and then 2.3, they want us to calculate the initial velocity of the tennis ball at the instant that it's released. At the instant that it's, so we've already calculated that, okay, which means we've used a very long approach, which has already even answered the next question, but it's fine. So we say this is a 0, vi squared plus 2 times the 9,8 negative times the 0,9. Okay, and what did we say? We just transposed that. So vi squared is 17,64. And then when we took square roots, our vi became 4,2 meters per second. There's no harm doing that again, as long as it's going to give us the max that we desire. Remember, all questions normally have different approaches, quite a number of approaches. Then 2.4. Now they want us to sketch a velocity time graph. Okay, they gave us a position time graph, they want us to sketch a velocity. So we said velocity is always made up of straight lines, no curves. Okay, then I can put my time somewhere here, which is in seconds. So if this is the origin, what was the initial velocity? The initial velocity was 4,2, the one we've just calculated in the previous question. And then it took some time, which was 0.42 seconds, sorry, 43 seconds to get there, which we can label as our T1. And then the graph continues. So it's just a straight line from here into that sort of direction. We don't need to mark this off as 0.43. You can if you have time, no problem. So it's calling this point A, where the ball started from, and then point B, which is more like the maximum height. At the maximum height, that can be point B, and so on and so forth. So after the maximum point, this section just tells us the direction or the velocity of the ball when it's falling down. So that is what one would do. Someone say, all of this for 4 marks. Yes. For as long as you have a straight line, not a curve, you get a mark. Then for as long as this part is shorter than the other part, because remember, this A to B is just the section from point of release up to the maximum point, which was quite a small distance. Okay, and then the 4,2, for as long as you've indicated it, you'll also get a mark. And then the time T1, which is the 4,3, you get the last mark. Okay, then let's look at question number. We need to do this because I feel like it looks more or less the same as what we've done, but it's fine, not a problem. We can look at it. Then question number 3, they're telling us that the sketch below shows the motion of a ball that is thrown vertically upwards from a balcony, and it takes 0.4 seconds, okay, to reach the highest point, after which it falls down past the balcony, boom, up to that. Then from the graph, how high is the balcony from the ground? So the ball is projected from the balcony, which means the distance from here up to there. That's how high the balcony is. So it's just 8 meters. And then 3.2, without any calculation, what is the numerical value of T1? T1, somebody? Remember, this is more like a parabola. And this 0.4, where the time is at the maximum, or the velocity is 0, that is the maximum height. This is acting as our axis of symmetry. So if this is 0.4, even this must be 0.4. So which means that is 0.8 seconds without any calculations. So that is just the logic. And then 3.3, they want the initial velocity. So we shall use more or less this, can use the first equation and say V final is equal to Vi plus A delta T, the initial velocity. So we can use the final velocity at this point of the maximum. Okay, so I'm gonna take the V final to be 0. Vi is what I need. I'm gonna say plus, I'm gonna use negative 9.8 times my delta T 0.4. Okay, so 9.8 times 0.4, I'm getting 3.92. Okay, then vi minus 3,92 is equal to 0. Then move it that side, which means the initial velocity is 3,92 meters per second. Which direction? It is basically upwards. It's upwards. Okay, and then 3.4, they want the maximum height above the ground that is reached by the ball. Now, since they're asking for maximum height, that is like displacement. Which displacement formula can we use? We can use. I don't know. Let's use the second equation, which is delta y is equal to vi times delta t plus a half a and then delta t squared. I think this can work. So they want the maximum height above the ground, so we're looking for delta y. So what is our initial velocity? We got it as 3,9. So guys, regardless of what value you get, for as long as that value is going to be used in the next question, please use it, even if it's wrong. Okay, it will do you some good for consistency's sake. So the time was 0,4 seconds plus a half. Since the direction of projection was upwards, going to be negative 9,8, and then we're saying we're multiplying that by 0,4 squared. And I use my machine. 3,92 times 0,4 plus a half times negative 9,8 times 0,4 squared. I'm getting 0,78 meters. So this is just from the point of projection. So 0,78. So just from here up to there, that is 0,784. Now, since they're talking about from the ground, the distance from the ground or the height from the ground, it's going to be the 8 plus the 0,784, which becomes 8,784 meters. And then lastly, no, it's not lastly, 0.5, calculate the magnitude of the final velocity of the ball when it reaches the ground. Okay, so in this case, we can look at number 1, either break down the journey into 2. Someone may choose to focus on the second part of the journey of the ball, which is like from the maximum point up to here. Since we know that at this point, the velocity is 0, so which means this will be our initial velocity, and we're looking for the final velocity, which will be 0. This one, the initial velocity. The time it took, we don't know, but we can get an appropriate formula. Or alternatively, someone can take the entire journey of this ball and then still get to the same result. So in this case, I'm just going to look at just from the maximum height, the first scenario. So if I use Vf squared is equal to Vi squared plus 2a delta y. Since I know my maximum height, I can use that. So they want the final velocity. So this is Vf squared. Initially, at the maximum height, the velocity was 0. So that's going to be 0. Plus 2. Our acceleration is negative 9,8. And then our height is 8,784. You could round that off to 2 decimals, there's no problem. So that is 2 times negative 9.8 times the 8.784. I'm getting, does that even make sense? Yes. I'm getting negative, no. If I use negative, then that means I'm using the initial root. But if I'm focusing on just the section from the maximum to, then it's meant to be positive. So that is 172,1664. That is Vf squared. And then I can find the square root of that. Square root, my answer, I'm getting 13,12. Okay, that's 13,12 meters. So that is going to be our maximum velocity or terminal velocity. So we said alternatively, someone can use that other route of the entire journey. Okay, so if you're using the route of the entire journey, then your displacement is just gonna be 8, because from the point of projection up to the same point of projection, the displacement is gonna be 0, and then we focus on just the 8. Okay, if we try that out, we said our initial velocity. Now let's try it out and see. Maybe let me just jot it down here. Just for the sake of space, I'll erase it. Okay, I'm using just the same thing. Vi squared plus 2a delta y. So we got our initial velocity as 3,92. That's what I want to use. So 3,92 squared plus 2 times now negative 9,8 times 8. 3,92 squared. Is this gonna make sense though? Something's fishy, something's fishy, something's fishy here. Guys, no, it's okay. Let's just ignore that and just use that formula. There's no need for second option. How does it test that? It's okay. Then 3.6, they want us to draw a velocity time graph. Okay, so if this is the velocity, and then that is the time in seconds, velocity in meters per second of the motion of the ball, indicate the following: initial velocity, final, and the time taken to reach the maximum. So our initial velocity, we said, was 3,92. Okay, and then the final velocity, we said it's 13. We said at maximum, what is the time? We said that was 0,4. So we're just gonna draw a line. It must be longer. And then we can put the 13 down. Then we can call this 13,12, but in the negative. Okay, it's not a big deal for as long as you have the initial or you have these 3. It's a mark for each. Okay, then we move on to the next question. Question number 4. Question number 4. What do they want us to do? They are telling us that a boy kicks a ball, okay, vertically upwards from a height of 0,6 meters above the ground. Then the ball moves past the top of the building 21 meters higher than the original point from where it was kicked. And then the ball hits the roof in 3,1 seconds after it was kicked. Then the ball bounces off the roof and then it comes to rest. So the ball is kicked, it goes up, past, reaches maximum, hits the roof, bounces off, and then it gets to rest. Okay, then they're asking us to write down the magnitude and the direction of the acceleration of the ball at point X. Where is point X? So point X is not indicated on the question, but regardless of where that point is, even if it's there, even if wherever it is, I don't know whether it's that. So that's gonna be just 9,8, and the direction must always be, we say, downwards, for as long as it's gravity, as long as it's free fall. Sorry, it's 9.8. I'm sorry guys, it's 9.8 meters per second squared. So now what about the units? Then 4.2, calculate the magnitude of velocity with which the ball was kicked. So we're looking for the initial velocity. What do we have in question? We know that this is 0.6 above, so which means the ball is going to travel 21 meters from where it was kicked. Okay, and it takes 3 comma where the ball hits the roof of the building, 3.1 seconds after it was. Okay, so I'm gonna look at the 21 from there up to there and then see. So if I look at my downward motion as positive, I can use delta y is equal to vi times delta t. Can use a half a delta t squared. Why? Because the question is asking for initial velocity, which is the vi. Only thing we have is the time and the displacement. Okay, so my displacement is gonna be 21, which is negative. Initial velocity, I don't know. My time was 3.1, and then a half. My A is gonna be 9.8. Oh, why am I doing that? It's okay. And then the t is 3.1 squared. I'm using negative 21 because I'm taking the downward motion to be positive, which means my displacement when it moves up will be negative. I am not necessarily focusing on the g. Okay, when I do the substitution of all of this, I have a half times 9.8 times 3.1 squared. That's gonna give me 470. Okay, no, not 470, sorry. It's 9.8, it's 47. So the whole of this is giving me 47,089. And then I must move it that side. So say plus 21, which is like a 68,089. And then when I divide this by 3.1, I'm getting 21. So initial velocity is 21,96 meters per second, or any other acceptable option or equation can be used. And then calculate the maximum height that the ball reaches above the ground. Now, since the initial velocity that we're focusing on is 21,96 meters per second, they want us to get the maximum height, and we said at the maximum height the final velocity must be 0. We're looking for delta y. Okay, so we can use v squared, v final squared is equal to vi squared plus 2a delta y. Our v final, that is a 0, is equal to, I'm gonna say 21,96 squared plus 2 times our a, which is 9.8. I'm gonna call it negative because I'm taking gravity to be downwards. Okay, now I move it that side, it's gonna be 19.6y. What is 21,96 squared? Getting 482,2416. Then divide by 19.6. Divide by 19.6. That cancels out. and then my y becomes 24.60 meters. So this is the maximum height that the ball is gonna reach. And then 4.4, we're being asked is referring to the sketch. Refer to the sketch and state whether the collision of the ball on the roof is elastic or inelastic. So since the ball reached the maximum height, it bounced off. Okay, so wait a moment. Is that question done? Calculate the maximum height that the ball reaches above the ground. Above the ground. We're not done. This 24 is, so remember, the ball was kicked from a height of 0.6. So which means we have to add the 0.6 also. Sorry. Plus a 0.6. Then that becomes 25.2 meters. Thank you. Then 4.4. We were saying the ball is gonna reach the maximum height and then it drops to the roof. Just one bounce and then it comes to rest. So is it elastic or inelastic? So I'm gonna say it's inelastic. The reason being, from the maximum height, the ball bounces, but the bounce just reaches a height that is lower than the maximum and then gets to rest. So we can say that the ball just does the bouncing. Ball bounces lower. Lower than the maximum height before. Lower than the maximum height that was reached. So I did mean that the ball decided to bounce higher, then it was going to be elastic. Okay, and then 4.5, they want us to sketch position. Remember I said position is a curve. Okay, position is measured in meters, and then time is measured in seconds. Okay, position time graph for the complete motion of the ball from the moment it was kicked until it comes to rest. Okay, so if I'm to look at it, remember the ball is gonna reach the maximum. We say 21. So if it says 21, okay, we have 21. And then which other height do we have? Okay, 4.2 minus 24.6 minus 21, which is 3.6, which means the height of the bounce is 3.6. So in other words, it went up. This is gonna be like 21, and then there's an extra 3.6 for it to reach the maximum where the velocity is 0. So I'm gonna take this to be my 21 negative. Okay, and then to just move, it reaches a maximum height of how many meters? 3.6, because we say 24.6 minus the 21, which is 3.6. Okay, and then it bounces off. They told us the bounce takes place at a time of 3.1 seconds. Okay, and then it takes also another bounce Do we know that time for the next bounce? We don't know it. But it does before it comes to rest. So what we need is the initial starting point, the maximum point it reached, and then that other point. Okay guys, so that is question number 4. Question number 5. Question number 5, I think I'll have to stop at a question below what I'd prepared. So this is more or less still the same, but it's okay, we can look at it. They're telling us that Sandile, who is standing on a platform, throws a small metal ball vertically downwards, vertically up from the height of 1,73 above the ground. So this is 1,73 up. Okay. At this velocity, the ball travels past the top of the building and returns to the hand, who is still at that same height. Ignore the effects of friction. Sandile is somewhere here. So with what speed does the ball strike Sandile's hand? So the ball was projected at 8. So since Sandile is still just at the same point, we're gonna say it's 8 meters per second. Nothing changes. Since we are ignoring friction, it's just gravity that is doing the work. Okay, using the equation of motion and not energy principles, calculate the maximum height that the ball reaches above the ground. So Vf is gonna be 0. V initial, we have it as 8. A, which is G, is 9,8, and then the height is what we're looking for. So I'm gonna say Vf squared is equal to Vi squared plus 2 times acceleration delta y. Then we say that maximum height velocity must be 0. 0 squared, initially it's 8, and then since I'm projecting it upwards, it's gonna be negative 9,8 times the y. So 2 times 9,8, that's 19.6. I'm gonna transpose it that side. So 19,6y is equal to 8 squared, which is a 64. Then I divide by 19,6. Okay, 64 divided by 19,6, I'm getting 3,27. 3,27 meters. That is from the point of projection. Okay, from here, or from wherever Sandile is, up to there. But now from the ground, since the question is talking about the ground, which means I'll have to add the 1,73 meters, which will make it, I don't know guys, help me, 1.73, which is 4,9995, which is, we'll round it off, it's just gonna be 5 meters above the ground. 5 meters above the ground, 5 meters above the ground. Okay. And then 5.3. So if a window on top of the building, on the top floor of the building is at 2,5 meters, calculate the time it's gonna take for the ball from the moment it was thrown to pass the top of the window on its return. So this is a quadratic, guys, a quadratic time it takes to pass the window. Okay, let's see. So we must be able to get at least two values if possible. So we can start by I doing what? We need to get the final velocity first of all, because in this case we're not focusing on the maximum height. We just want the velocity after the 2.5 meters of distance traveled by the ball. So that's going to be 8 squared plus 2 times 9.8 negative times the 2.5, because that is the distance from Sandile's hand to the window. Okay, when you sort this out, 8 squared plus 2 times negative 9.8 times 2.5. Oh Lord, what's going on? I'm getting 15 and square root of 15. So this is 15, and then square root of 15 is 3.873 meters per second. Okay, this is like our final velocity. And then if I use Vf is equal to Vi plus 80 or A delta T. Our V final, we have it 3.873. It's going to be negative. And then our initial velocity was 8. Our acceleration is negative 9.8 times a certain time. Okay, so when I move the 8 that side, it's gonna be minus 8, which is, I messed it, 3.873 plus 8, that's 11.873. Negative is equal to negative 9.8. We now divide by 9.8 over 9.8. That cancels. What do we have? Getting 1.21 seconds. So they say every the time taken for the ball from the moment it was thrown to pass the top of the window on its return to Sandile's hands. So I'm getting 1.21 seconds. Okay, the reason as to why I'm using the 2.5 is because that top part is gonna cancel out to be 0 in terms of the displacement. Okay, since this part is gonna be the positive displacement and then this negative displacement is gonna cancel it out. That's why we're gonna just stay with the 2.5 meters. Then 5.4, taking upward direction as positive. Draw a sketch of position. Time again. Guys, we said position is a curve. Taking upward as positive. Time is in seconds. Okay, so if we take our position in that sort of format, what do they want exactly? They want us to draw the ball's motion from the moment it left Sandile's hand until it lands back into his hands. Oops, okay. That is 0. That's pretty easy. Something like that. So what is the maximum height that, or the maximum position that we got? Somebody help us. It was 3.27. 3.27. So just indicate this. 3.27. Is there time that is needed? How long did it take? Do we know that? Is the window calculator taken? And that is for the window. Nothing. So you can just leave it like that. So for as long as we have the correct 3.27, as long as the shape graph starts from 0, because that's our displacement, the ball was not moving at that point. As long as the shape is correct, and then we label this correctly with the correct units, then we're good to go. question number 6. I don't know. I feel like we should skip this, or I don't know. Skip it, do it. It's fine. Let's attempt it and see. So ball is thrown vertically upwards at the velocity of 4 meters per second. 4 meters per second from the roof of a building with a height of 10 meters. And then the ball strikes the ground and rebounces to a height of 3 meters. Okay. Okay guys, let me work this out, but if the next question is more like the same, I'm gonna skip it, so that we look at just a different sort of scenario. Okay, so they want us to get the time taken for the ball to reach the maximum height. So we said maximum height, final velocity is 0. So our initial velocity is 4 meters per second. Okay, the ball strikes and rebounds to a height of 3 meters. So this is pretty quick. We can say Vf is Vi plus A delta T. Our V final is a 0. Our initial is 4. Since we're throwing the ball upwards, it's going to be negative 9,8 times T. Move the 4 that side, which is 9,84. So 9,8 T is equal to 4. And then divide both sides by 9,8. 4 divided by 9,8. I'm going to get 0,41 seconds. Let's round that off. And then they want us to get the maximum height that the ball reaches. So the maximum height, we need to get an equation that involves displacement. So I can use what just happened? Okay. So I'm saying I can use my delta y is equal to Vi delta T plus a half A delta T squared. I want the height. Do I have the time? Yes, the 0,4. Acceleration, I have it. So it's going to be 4 times 0,41 plus a half times negative 9,8 times 0,41 squared. I hope that makes sense. 0,4 plus 0,5 times negative 9,8 times 0,41 squared. I'm getting 0, is that true? Let me just redo it again. 4 times 0,41 plus a half times negative 9,8 times 0,41 squared. Okay, I'm getting 0,82 meters. Okay, so that is our maximum height. And then they are telling us that the ball strikes the ground 1,09 seconds after it was thrown and remains in contact for 0,2 before bouncing off. We need position versus time. Use the ground as a reference and indicate the following. So when they say indicate the following, this is what they're going to mark. Okay. So this is position in M. I'll say this is my time in seconds. So if that is a 0, at what point did the projection start? This ball was projected from 10 meters. So which means our story must start from a height of 10. Okay. So we're saying, I don't know, let me just throw something small. That's a 10. And then this ball is gonna move up to the maximum. What do we get as our maximum height, guys? It was 0,82. So 10 plus 0.82, that's gonna be 10.82. And then this moves. Okay. It hits rock bottom. They are telling us it spends some time. So at what time does it hit the ground? Strikes the ground at this. So this is 1.09. Okay. It stays on ground for 0.2. So 1.09 plus 0.2 is gonna be 1.29. Okay. And then it just bounces off. To a height, did they give us that height within the question? Yes, to a height of 3, which means this graph must stop at 3. So this must be at 3. So just that. As long as you represent the height from which it was thrown, it's a mark. Maximum height reached is a mark. The height reached by the ball after bouncing, the 3 meters, so it's a mark. And then the time it takes to strike the ground, it's a mark. Contact time, it's a mark, because the difference between that will be your 0.2 seconds. Okay guys, that is question number 6. Question 7. Okay, this is interesting. This is interesting. Telling us that ball A thrown vertically upwards from the top of the building, that is 8 meters high, at the velocity of this. At the same instant, there is another identical ball that is thrown upwards. So this goes down, and then this one goes up. Okay, it's thrown at the same kind of thing. So I'm gonna just summarize this and say ball A and then ball B. The height, initial velocity, I'll say VI for both balls, telling us A is at 12. At the same instant, B is thrown upwards with a velocity of 30. A and B pass each other after time. So they will be equal, or the distance traveled will be equal after this amount of time. Then give the direction and the acceleration of B while moving upwards. So one thing we said, they want the direction. We said direction of the acceleration. Acceleration will always act downwards. Okay. Then they want us to calculate the velocity of B, ball B, the moment it passes ball A. The velocity that A or B passes A. Okay, so I need to get the final velocity first of all. Final velocity that B is gonna be traveling with. So I'm gonna say V initial plus A times the delta T. Okay, so my initial was 12. Said calculate the velocity of B. Guys, I'm sorry. We're looking at ball B, which is 30, not 12, plus the 9.8, which is gonna be negative. And then what distance is traveled? We said ball A and B pass each other after 2.13. So I'm gonna multiply that by 2.13 because I know they're gonna meet or they're gonna pass each other after 2.13 seconds. Then I'll do my substitution into the calculator. 3 plus negative 9.8 times 2.135, which is 9.077, which can be rounded off to 9.08 meters per second. Which direction? It's moving upwards. Okay. Then calculate the distance between A and B, 2.5 seconds after it was projected. After it was projected. Okay. So I'm gonna use delta y is equal to vi delta t plus a half a delta t squared. Since they're asking us for distance, we know the vi, we know the t's. Okay, they gave us the t as 2.5. Acceleration, we know it. Okay, so I'm gonna look at probably both balls and see what's going on. There's ball A and then there's ball B. So if I focus on A, my displacement is gonna be our initial velocity was at 12, and the time that we're looking at is 2.5 seconds. And then plus, remember ball A was being thrown downwards, so the 9.8 is gonna be looked at as positive. And then times 2.5 squared. Okay, 12 times 2.5 plus 0.5 times 9.8 times 2.5 squared. That is giving me 60.625. 60.625 meters. So that is how far ball A would have traveled. And then when I look at ball B, okay, if I look at ball B, let me say what is 80 minus 60.625, which is 19, something. Oh, that makes sense. Calculate the distance between A and B. After this kind of time, let me just dissect this. So this would have traveled that much, which is 60.6 something. So what is left is 19.375. Okay, now I'll visit that again. Let me look at B. When I look at B and use the same kind of approach, it's gonna be my 30 times 2.5 plus a half times negative 9.8 times 2.5 squared. Okay, saying 30 times 2.5 plus a half times negative 9.8 times 2.5 squared. That gives me 44.375 meters. So this is above the ground. That is above the ground. Okay. Let me just do this. Okay, so I'm gonna look at B. So if B has traveled 44.375 from the ground, and we are saying A traveled as far as the 60, something and reached here, and what is left below the ground, we said it's 19.375. If I get my 80 minus the 60.625 to get what is left at the ground, so that for me to get what is shorting, I'll focus on the 19, something and this 44. I subtract the two to get the distance between. So 44.375 minus the 19.375, and then I get 25 meters. So it's just 25 meters between the two balls. Okay, then they want position time. Oh Lord, these people have position time. So this is position in meters, and then we're saying this is the time in seconds. Okay, so we have two balls, remember. One ball is starting from 0, another ball is starting from a certain height, which is 18. So this ball is gonna move in this sort of direction. Okay, I'm gonna use a different color for other balls. So which ball started from 0? It's ball B. I'll label this as a B. And then A started from somewhere there. And then it's gonna hit the ground. So we're saying at this point, when they pass each other, we were told that time is 2,135. 2,135 seconds. Okay. So for as long as we have this position in meters or displacement, delta y in meters, time in seconds, and all of that, then we're good to go. Then question number 8. We've seen this, guys. We have seen this. I don't know. I'll beg to skip it. Should I, guys? Yes, I think I'm gonna skip it because it just looks the same. When you look at our first question, when you look at the second question also, it's just the same sort of approach. So I'm not gonna do that. Let me just go to question 9 and wind up. Okay, so same question number 9. Ask this question 8. Next time. Okay, question 9. They're telling us there's a girl that stands on a platform in a classroom. She throws a ball vertically upwards to the floor, hoping that the ball, after it bounced on the ceiling, will hit the ceiling. What's going on? A girl stands on a platform in a classroom. She throws a ball vertically upwards to the floor. Okay, so this girl is standing somewhere here. Around source case, I don't know how to draw girls. Okay, she throws the ball to the ground, hoping that the ball, after it had bounced from the floor, it would hit the ceiling. Okay, then it's making sense. So she throws the ball with the speed of this. So our initial velocity is 8 meters per second, the height from above the floor. Okay, so that is the platform. Okay, we need to ignore the air friction, air resistance. Then they want us to write down the magnitude and direction of acceleration of the ball immediately after it left the hand. So acceleration, guys, it's a giveaway, this one. Direction, downwards. Acceleration, downwards, it's a must. The 9.2 is the motion of the ball while it's moving downwards towards the floor. Is it free fall? Yes or no? The answer is a yes. Since we are ignoring the effects of air friction, and this ball is just falling under the influence of gravity. So we are saying only gravity. It's only gravity that is acting on the ball. Only gravity acts on the ball. Or we can look at the influence of gravity on the ball, or the ball is moving under the influence of G. The 9.3, they want us to get the magnitude of the velocity with which the ball hits the ground. So magnitude with which the ball hits the ground, they want us to get the VF, final velocity. We said our initial was 8. Initial velocity was 8. G is 9,8. Do we have the time it takes? Anything? They only gave us the height. which means the displacement is, excuse guys, displacement is 1,8 meters. So we can use the VF squared. Yeah, VF squared is equal to VI squared plus 2A delta Y. We're looking for VF. Okay, so our VI is 8 squared plus 2, since the ball is dropped down, so it's gonna be positive 9,8, and then the height is 1,8. So 8 squared plus 2 times 9,8 times 1,8. That gives me 9 to 9. So VF squared is 99,28. Then I must find the square root. So square root of my answer is 9,96. Okay, 96 meters per second. So that is the final velocity when the ball strikes the ground. Okay, then 9.4, how long does it take the ball to hit the floor? So we're looking for the delta t. Since we have our VF, we can even use that first equation. The VF is equal to VI plus the A delta t. I feel that is way quicker. It's VI plus A times delta t. So our VF, we said it's 9,96, is equal to the initial velocity, which we said was 8, plus our acceleration, which is 9,8 t. Positive, since the ball is being dropped. Move the 8 that side. 9.96 minus 8 is going to be 1,96. 1,96, then divided by 9,8. So which means t is 2 seconds. Is it 2? Wait, 1,96 divided by 9,8 is 0,2. 0,2 seconds. Okay, and then the ball bounces inelastically on the floor. This simply means it's just gonna bounce off below the height of projection. So it bounces off inelastically on the floor where the speed of the ball decreases by 20%. And then the ball is in contact with the floor for 0,01 seconds. And they want us to determine by means of calculation whether the ball will reach the ceiling after it bounced off. So inelastically simply means the height kind of decreased compared to what was expected. Now, since they gave us 20%, they are telling us that it decreases by 20%. So someone can find 20 of the final velocity, which we got as 9,96, and then you subtract 9,96 minus this 20 over that. So it's 9,96 minus 0,2 times 9,96. I'm getting 7,97. Okay, that is 7,97. So this is gonna be the new velocity. Okay, they want us to determine whether it will reach the ceiling. Remember, our ceiling is at which height? 3,5 meters. So we need to find the displacement and see if our displacement is going to be 3,5. Okay, so if we get VF squared is equal to VI squared plus 2 times a. Oh god, so I think I'm tired now. I said a delta y. Okay, we're looking for the displacement. We have the acceleration, we have the initial, we have the final. Yes. So we're looking for the maximum height that the ball is gonna reach. And the maximum height, we said velocity will be 0. So 0 is the same as 7,97 squared. Now someone will ask, why are we using this? Remember, as the ball hits the ground, it spends some time there, the velocity decreases, and then the velocity with which it leaves, the velocity with which it bounces off. So let's say there was no 0,01 seconds. Then the velocity with which it hits the ground would be more or less literally the velocity with which it leaves. So in as much as it was the final velocity for the first journey, it's going to be the initial velocity for the next journey of the bounce. Okay, 2 times 9,8 delta y, it's negative since it's moving up. Okay, when I simplify that, 7,97 squared, I'm getting 63,521 minus 19,6 y is equal to 0. Move it that side, 19,6 y. Then divide both sides by 19,6. Okay, and then our y is going to be divide by 19,6. I'm getting 3,24 meters here. Okay, so since the maximum height I'm getting is 3,24, and they told us that the maximum height out of the ceiling is 3,5, which means this ball is not gonna reach the ceiling. Okay, so determine by means of equation whether the ball will reach the ceiling. So the answer is nope. The ball ain't gonna reach the ceiling. The ball won't reach the ceiling. Will not reach the ceiling with the target point. Alright, that is 9.5. And then 9.6, lastly, they want us to sketch a velocity time graph. Our first colleagues, this is velocity in meters per second. And then we're saying this is time measured in seconds. So if we look at velocity, remember we said velocity time graphs are basically straight lines. Now, at what velocity did the journey start? So it started with 8 because that was the initial velocity. We worked out our final and we got 9,96. Yes, 9697. It's 96. Use a different color. Okay, so this is 9,96. Sorry if my rounding off was poor. And then at what time was that? After how many seconds? It was 0,2 seconds. It was 0,2 seconds. We found it. Let's see. Okay. And then from this point, what happens next? There is a 9,97 when it is doing the bouncing off. So I'm gonna put it here, 9,97. So which means this is also 7. Okay, when it is bouncing off. So I'm just gonna have this line. to that point. And then I'm gonna have, they said it takes 0.01. So this is gonna be 0.21 seconds. So which means my line must pass the middle point, and this must correspond to this 9, something, and then it reaches 0, since it's gonna reach the maximum point of the 3.24. So straight line, then straight line. Okay, and then lastly, question number 10. Telling us a boy throws a ball vertically into air from the top of a building, and then the ball strikes the ground after 4.08. The velocity time graph is being drawn for the entire motion. Ignore the effects of friction. Okay, there is our definition question. What is a projectile? You said projectile was any body that was under the influence of acceleration due to gravity. So a body, or we can say an object that is acted upon by only acceleration due to gravity. Acceleration due to gravity. That's the only force. I'm sorry guys, my English, my repetition things. So an object that is acted upon by acceleration due to gravity, strictly acceleration due to gravity, is a projectile. Then what is the acceleration of the ball at 1.02 seconds? Remember, this is a velocity time graph. Okay, and for us to get acceleration is change in velocity over the change in time. You can use those formulas, equations of motion, but there is no need for that. Okay, so if you look at the change in velocity over the change in times, is 9.8 divided by 1.02, getting 9.61 downwards. Okay, that is if I'm to use the graph. Okay, acceleration of the ball at this time. So it's a two-way thing. Since we said an object acted upon by only acceleration due to gravity is a projectile, and this thing is just showing us the velocity time graph, and then they ask us for the acceleration, which means someone can say it's 9.8 meters per second squared downwards. But if we are to use the figures on the graph, change in velocity is going to be 9.8 over the 1.02. How are we getting the 9.8? Remember, we're getting the change, the gradient, change in V over the change in T. So that is what is giving me the 9.6. So it's fine, whichever option you go for, it's correct. So this 9.6 is taking into impact or into effect the values or the effects of frictional force. That's why it is even smaller. And then 10.3, they want us to get the displacement of the ball. So the displacement, they want the delta y. Okay, we know that delta t is 4.08. Okay, so I'll say delta y is the same as vi delta t plus a half a delta t squared. Our initial velocity was it 0? No, it was 9.8. The starting velocity was 9.8. So that's 9,8, and then the time that we're focusing on is 4,08 plus a half. What is happening to the object is thrown into from the top. So I'm gonna take it to be negative. And then the time is still 4,08 squared. So when I punch that into the calculator, 9,8 on that, I'm getting 41,58 negative. So which means the displacement is downwards, 41,58 meters downwards. Then they want you to sketch the position time, and those are the things to look out for. So I'll say y in meters, and then this is the time in seconds. So number one, where did the graph start from, or where did the object? So that is the 0. And what time did it reach 0? At what time was the velocity 0? It's after 1,02. So 1,02. The displacement was 0, or the velocity was 0, so that's the maximum displacement. And since it's more like a parabola, twice that is going to be 2,04. Means the graph must also pass through that point. Then we need the time of 4,08, which is twice that. So it's going to be, so this is the maximum height. And displacement is 0 at that time. Then this graph continues. So guys, I'm horrible at drawing. Let's do this. Okay, thank you. Something like that. So this position here, this displacement is what we just calculated in the previous question at a time of 4,08. Our displacement was 41,5 something. 41,58. 41,58. Okay. So 41,58 meters. Hey guys, for as long as you just show us the t values and the direction and everything, then we shall be good to go. And then other thing is about someone asked now, how about the acceleration time graph? How do they look like? So acceleration is not that hard. I'll just give you guys move. Erasing is not working. Okay, so if we have an acceleration time graph, it's just let's okay. So that will be acceleration, and then this will be the time. So it's usually just straight lines. So this is an acceleration time graph, depending on which acceleration you're taking to be positive. So this will be 9,8. So it's just uniform, since it never changes. Sometimes it can be drawn like this, and then like that, depending on how the object is moving. Okay, guys, I think that's enough for the day. What we haven't looked at, probably in the next episode. Let's meet. Hello and welcome to this episode of Physics